right. Well, pleasure to have our own Alexandru from Deep to speak about group irrationality and can logic help. Yeah, please go ahead.
Thanks, Jay. Yeah, so I haven't given till now a talk in a hybrid kind of version. Do let me know if people in the room have any questions. I don't know how this works. Probably they will have to pose to you, and then you relay them to me. All right. So I'll start. So this is a talk about work done in our group, joint work of me, mainly with Sonia Smets, but also other collaborators and also various students listed down there. Actually, there are more, but the slides did not fit. But I mean, the ones I'm going to cite are these. It's most of the stuff that or almost all the stuff that I'm going to present is not new work. So I apologize to the logicians that joined the group. You may leave if you want now. The reason is that this is a talk is mainly directed to the deep audience, in which I cannot assume that anybody they saw any of my old work on this topic, or also that they know much about formal logic. So on the other hand, I piled a lot of stuff. So as usual, for people who saw my talks, I have like 78 slides. So at some point, I'll start to go faster and faster and skip stuff. Don't worry. It just means they're not important, I guess. All right. So the topic is group knowledge, right? Or what I call the epistemic potential of a group. This is the knowledge that the members of a group may come to possess by somehow cooperating as well as they could, and using all the information they possess as much as they can. Now, what does it mean, a group to possess knowledge or sometimes beliefs, because they may be false or wrong? So one way to think is that you infer what the group possesses, because of course the group doesn't have a mind or a brain, although some people think it does. But you can infer it from the group's behavior, from the actions that the members of the group can perform, from the coordinated protocols that they follow. You can assign some kind of beliefs or knowledge to the group as motivating these kind of actions. And the idea is that they can have more or less such knowledge. And the first question is, does the group has more or less or the same as individuals that compose it, right, in the sense of knowledge? And since our group Deep is all about emergence, you can anticipate that the answer is, well, it's complicated. So yeah, agents can combine and aggregate their various pieces of knowledge by various ways, by communication, by inference, by some sort of statistical methods, by forms of judgment aggregations, such as voting, for instance. And then this creates new information that the group has that may not be already known by any of the individuals. So in principle, you would think, and in general tends to be true, that groups know more than the individuals, because some things can be group knowledge without being priorly known by any member of the group. But the problem is that opposite can also happen. That's what I will argue in this talk, that despite appearances or first impressions, some of the individual knowledge may be inaccessible to the group as a whole. So the usual assumption, the one that essentially the group's potential knowledge includes everything known by all its members and more. It's usually it's kind of known in the literature as the paradigm of wisdom of the crowds. And by the way, people do not distinguish much between types of such wisdom of the crowds. And I want to distinguish in this talk two different kinds, because the examples in the literature can be grouped under two very different kinds of wisdom of the crowds. each comes with a different explanation, and it's with a different form of essentially judgment aggregation. In real life, of course, it's even more complicated because these two types are mixed. In most real life examples, that you encounter a mixture of the two types. But for conceptual purposes, it's good to distinguish them. So the first type of group knowledge is based of sharing or combining private observations of what I called hard evidence, which essentially is like facts or things that are proofs or things that are absolutely certain. So they really deserve the name of knowledge in some sense. And you share them, the agents tend to try to share them. These pieces of hard evidence complement each other somehow. They fit like the jigsaw, like the puzzle, like in a puzzle, like a jigsaw thing. And in this way, you create the wisdom of the crowds. You generate more knowledge. So the examples are deliberation in a hierarchy committee, collaborations on a paper or experiment, joint authorship, or at the limit, this kind of big science projects like the Human Genome Project, classification of finite groups, even the proof of Fermat's last theorem, which is attributed to Wiles, but in fact, it's the end result of many, many lemmas proved in very different papers and a lot of conceptual work and proofs that nobody fully controls, no individual, and it's not the work of anybody in particular. So, so I'm talking about potential knowledge because you imagine this group before they share the information, right? So the knowledge is there, but it's not yet actual, right? None of them really knows the end result, maybe. And at some point they share all or enough of the information, and then this knowledge becomes actualized, right? So, so the actualization happens by communication within this group, all right? So the puzzle fits together, the key fits in the lock. I have the key, you have the lock, or many minds, as in this picture down here, get together, and here you go. And the standard explanation for this type of wisdom of the crowds is logical. It's essentially a concept in epistemic logic called distributed knowledge. It's logical because essentially you intuitively, you just put together, like as if you centralize in a database. You can imagine that all the knowledge of the various agents, and then you use logical inference to combine them, and that's how you get the group knowledge. All right. So, sorry. Here is the standard model for knowledge in epistemic logic. It's a relational structure. So consists of a set of states, like a state space, as it's called in physics. In philosophy, sometimes it's called a possible worlds semantics. So these states can be called possible worlds. They are essentially, each state represents a possible state of the world, or of the relevant part of the world, the one that we are talking about, like the system. We have a finite set of agents, A, and for each of these agents, there is given an equivalence relation on the, oh, this is a typo. So it's included in S cross S, not in A cross A. So it's an equivalence relation between states, right? Labeled by each agent A, right? And essentially, the idea is that you have a state S, you state W, and you have this tilde A between them, if and only if that agent A cannot distinguish between those different states. By cannot distinguish, I don't mean conceptually. He could, in principle, imagine the distinction. He understands the distinction because, for instance, one has P true, one has not P true. But the idea is that he cannot tell them apart. He cannot, if the real state is S, he doesn't know. For all he knows, it might be W, right? So these states look the same to him from the perspective of his information. If you like, the way economists, game theorists package this stuff is slightly different. They package as a partition. And mathematical and equivalence relation divides the space into equivalence classes, and those form a partition. So these two descriptions are equivalent. And this is called the information partition of agent A. By the way, there are variations in the literature of this. I may mention later. Maybe I should skip the details, but so sometimes there is something called Doxastatic models. These are models for belief, while epistemic models are models for knowledge. So doxastic models essentially emerge by relaxing the conditions on these relations. Instead of assuming that they're equivalence relations, like reflexive, transitive, and symmetric, we assume something less, like asymmetric, possibly irreflexive, and so on. And there are some standard assumptions that I mentioned here, transitive, Euclidean serial, whatever that means. It's not very important. But when we have such weaker relations, they capture a notion of subjective possibility, like state S looks to agent A as if it might be W, but it might be not be actually in reality, right? So he might be wrong. So there are models of belief. Another variation is probabilistic epistemic models, of which hopefully I will be able to explain a bit more if I get there, because it's somewhere towards the end of my slide. Essentially, they are obtained from these partitional models, the equivalence relation epistemic models, by adding probabilities, one for each agent, right? So, and those probabilities sum up to one within each cell of the partition, right? The different cells are different they are distinguishable, right? So if two worlds are in different cells, this means the agent can tell them apart. So if one is the world, the other, he knows the other one is impossible. For other agents, they might be in the same cell because the partition depends on the agent. So then they are equally possible. And an agent only puts probabilities, so to speak, locally on each cell, like they sum up to one in that cell. Yeah, they express how likely is that state according to each agent. We'll see details more later. And here are some definitions, again, very standard. This symbol here is satisfaction relation. It's a way for logicians to be pedantic, and instead of saying truth, they just put this relation. So it's a relation between sentences or formulas on the right and states on the left. And essentially it says the formula on the right is true in the state S or at state S in that verb. So what this says, it says this formula that says agent A knows some proposition phi is true in a state S, if and only if phi is true in all the states that look the same to agent A, right? In other words, in all the states that belong to the same cell, partition cell or equivalence class as that state S, right? Because the agent essentially only sees the cells. He doesn't know more. He cannot distinguish more within the cell. So for him to know phi is to be true throughout the cell. It may also be true outside the cell in some other cell, but it doesn't matter. As long as it's true in all these worlds that are equivalent for him, then he knows phi because he's in control. And now the notion of distributed knowledge that I talked earlier is one of the numerous notions of group knowledge in the literature, in the epistemic literature. There are two standard ones, distributed knowledge and common knowledge. So these are notions of group knowledge. So you got a group, a set of agents, G, and this dk sub G and ck sub G, this is common and distributed knowledge. They are defined exactly the same as individual knowledge with the same, essentially the same clauses almost, except the equivalence relation, sometimes called indistinguishability relation for agent A, is replaced by some appropriate group relations that say, for instance, for distributed knowledge, you use this tilde sub G, which is the group indistinguishability relation. So it's a relation between states that says nobody in the group can distinguish the two states. No agent in the group can tell them apart, right? So, so in other words, this relation is the intersection of all the indistinguishability relations of all the agents in the group. And using that instead of the original relation, you define similarly distributed knowledge. So essentially, this notion of distributed knowledge corresponds to some kind of, the easiest way to define some kind of potential group knowledge, right? Because essentially, intuitively, something is distributed knowledge in a group G if that something can be recovered by pulling together all the information possessed by the agents in G and applying logic to derive everything that follows from it. And if nobody can tell apart these two states, then the group cannot tell them apart. So then whatever is true in is more refined. So this gives you a more refined partition than the original one, right? The cells of this equivalence relation. Capturing the intuitive, the idea that the group knows more than the individuals, potentially. I mean, can be more or equal. Now, the common knowledge is different. It's actually less than what the individual agents know. So it's what's common between them, right? So it's what the whole group knows in the sense of like, knows, I know it, you know it, I know that you know it, and so on. We all have it in common. These are things that are much less known. I mean, much less things are known in this way than my own knowledge. I have some secrets that you don't have. Those are not common knowledge. You may have some, Jay have some other secrets. Those are not common knowledge. But for instance, the fact that we are all part of this Zoom talk is common knowledge, for all, at least for all practical purposes. Because of course, it might be possible that without me knowing, somebody might have dropped out of the Zoom. So then it's less certain. But assuming everything works out, it's common knowledge that we are doing this Zoom together. So the common knowledge is defined again similarly, but using this tilde super G relation, which is a bit more complicated in the first one, because it has to implement this idea that it corresponds to what is true, what is the case, what everybody knows that everybody knows, and so on and so forth. And the formal definition is here for this common indistinguishability. It says you take the union rather than intersection of all these relations. You have identity, you have all the equivalence relations for the agents in the group, you have all the concatenations of two, or concatenations of two such relations and compositions in any order with any two agents in the group, and so on, concatenations of three. All right, so that's the definition, and captures this notion that this is common knowledge of the group. Now, the logical basis of the first type of wisdom no crowd is very simple to explain. You can use a model transformer. That's the way we do it in a branch of logical dynamic epistemic logic. So a transformer, a function that takes an epistemic model, the one I described, the type that I described, and returns another one for a given any group G. And the transformer is called in this case bang G, like exclamation mark G. Some people call it resolution. I call it sharing. So everybody in the group G shares information with everybody else in the group G instantly, and we assume the communication is fully secure. They all get it. There is no uncertainty about that. They all know that the others get it, and so on. So as a transformer, what does this do? Leaves the model the same as the initial one, except it changes the equivalence relations for each agent into one, for each agent in the group G. All these relations become one relation, because since they centralize the information, they get this tilde sub G, which, remember here the definition is the group indistinguishability, right? So now each of them can distinguish the things that anybody else could have distinguished before, right? And so their indistinguishability is the previous group indistinguishability, right? So that's the only change, and it affects only the agents in the group. The agents outside the group keep their own relations. So that's the model transformer. It's a very simple one. All right, so there is something that I don't want to explain in detail, namely these square brackets here. This is called a dynamic modality or dynamic operator. And essentially it's a propositional construct like negation, or like this decay. But it applies to a proposition that comes after it, produces other propositions. But what it does, it looks into the future. So it actually tells me that to evaluate the truth value of the proposition that follows, but not in the current model, but in the updated model, the one obtained after the model transformer is applied, right? So essentially says, intuitively says, after this action of resolution, in other words, after everybody in the group G shares everything with everything in the same group, then the next sentence is true, whatever follows from it. And this implication here, it's a valid, it's a theorem, if you like, of logic that says if P was distributed knowledge to start with in this group, then after they all share their information in the group, P becomes common knowledge in the group. Which it's natural, I mean, it's like almost obvious should be. Not only they know it, each of them, what used to be this distributed kind of potential ghostly knowledge of the group, now not only is internalized by each of them, they all know it, they all know that the others know it, and so on. Because this this sharing was done publicly. So this theorem, if you like, is the logical basis of the first type of wisdom of the crowds. It's a very simple phenomenon in itself. All right, now I move to the second type. The second type of group knowledge is very different. It involves opinions or beliefs, if you like, of each individual agent that are based on private, independent observations of some pieces of evidence, but those pieces of evidence are soft rather than hard evidence. What does it mean? It means they may lead them also sometimes to wrong opinions, to false beliefs. So they are not certain to indicate the truth, right? They give you some typically truth-like things that maybe approximate the truth, but maybe not fully. All right, so this is the first thing, right? The first thing is that they have these independent private observations that point to some conclusions. There are some beliefs that each has. However, those beliefs are not guaranteed to be true, and they may even be mutually inconsistent, contradictory. So I may get evidence that points towards P, you may get an evidence that goes the other way around. Right? So it's not easy to combine them then, because you cannot use logic to combine it because you'll get a contradiction. And the next step is the way they are aggregated, these beliefs. It's not by logic and it's not by communication. It's not like I'm telling you everything I know, you tell me everything you know. No, they are aggregated, so to speak, externally by some referee or in a different, for instance, by voting. So each has an opinion, P or not P, we vote, and then there is a mechanism to produce the group conclusion. For instance, majority rule, or unanimity rule, or some other rules proposed in social choice theory. But we don't have to share all the information. I don't tell you my reasons why I believe P. Maybe because my reasons are so complicated, there's a long sequence of observations that I made that's way too much, or my life experience, or whatever. So we only the beliefs, the conclusions, the opinions are integrated in this external way. And it's essential that there is no prior communication to this aggregation. So before this pulling together by voting or sharing, by voting, externally, there is no communication allowed. This is in order to ensure complete independence of opinions. The opinions are only based on these private experiences. So examples of such, of course, that's an idealized setting. In reality, things are not so smooth, but that's what you would like to have in this second type of wisdom of the crowd. So examples of this are, for instance, replication of experimental results. Right? Some group does an experiment, announces some conclusions, and the others independently, without disregarding altogether that stuff, without any communication, they redo the experiment in their own way. And if they agree, then great. If not, well, navigating a maze, that's a famous experiment, Norman Johnson. You have a complicated maze and you put people independently one by one, you place them somewhere, say in the center of the maze, and they have to get out. And it takes them a while, they try, and eventually they get out by trial and error, each individually. They don't talk to each other. All right, that's the first test, the first thing. Second, you put them again. Each of them goes again. Now they have some information because they had some life experience, some private experiences or evidence, namely their memory. They remember, okay, here I was going right and didn't go well. Maybe now I turned left. Here was, yeah, after that I was out, so I should turn. So each does it again, and now they do better than the first time, of course, because they have this more evidence. Not perfectly, of course, but the interesting thing is not that. The interesting thing is that the experimental, so he plays the role of the counter, the one that counts the votes, right? Marks at each turn. So let's suppose in this maze there are always at each intersection there is a right turn and a left turn at each crossing, and they have to choose right or left. So at each turn, the experimenter notes down the number of people who on their second trial turn right, and also knows the number of people who turn left on the second. And then marks in red the turn that belongs to the majority, that the majority took. And here you go, if you have many people, the path described exactly by the turns taken by the majority tends to be the minimal path out of the maze, the best essentially escape route out of the maze. That's what experiments show. And of course, it gets better if there are more people in this trial. This path, mind you, might not have been taken by anybody. Like nobody might have done exactly the minimal path, no individual. So like in the first type, there might be things that nobody knows in the group, but somehow the group knows, right? Because this path describes in a way the collective wisdom of the crowd, and tends, after a lot of people tried, to get the perfect, the minimal escape route, which is kind of amazing. Another example is prediction markets, but I will not go into that. Here is a more artificial example made, well, also done in the laboratory, but was made with the purpose of analyzing this phenomena in an easier way. So we have a room, and in the room, it's known to everybody that in the room there is one urn, only one urn, but that urn was chosen, say, randomly with a coin between two different types of urns, namely urn W and urn B. Urn W has majority white balls in it, let's say 2 white balls and 1 black ball, or twice as many white balls. And urn B is the other way around. One and only one urn has been placed into the room, somehow randomly, and that's known to everybody. Right? And now there are lots of people waiting at the door, and you introduce them one by one into the room. They are allowed to draw randomly one ball from the urn, look at its color, put it back, and then they have to make a guess which urn is in the room. So the private evidence is the color that they see. They also know the setting, and they have to make a guess, informed by their evidence. The guesses are kept secret forever, so there is no communication allowed. But somehow they are recorded by the experimenter in a big book. Right? So these evidences, these beliefs are, this means they are completely independent of each other. People never talk. At the end, the guesses are externally aggregated by majority rule. So the experimenter counts the number of, let's say, so by definition, the majority guess, the guess W or B that was belonging to majority, we'll call it the virtual group knowledge, right? The group knowledge or belief, if you like, because it might be wrong. And here you go, both experiments and theory will show that when the size of the group tends to infinity, so the bigger, the better, the group's virtual knowledge actually matches the real state, the real urn, W or B, with a probability approaching 1. So with a very high probability, if you like, the higher, closer to 1, the more the size of the group is larger. Now, the explanation for this second kind of group wisdom is very different from the first one. It's not logic, it's statistical. Essentially, it's some variation of the so-called Condorcet jury theorem, which I'll explain in a second. And essentially underlying it, and in the proof, it's is based on the strong law of large numbers. Intuitively, what happens is that when performing, the same as in this maze example, when performing many independent observations, the individual errors, or if you like, the private pieces of evidence that support the false hypothesis, say urn B when in fact it's urn W, will be outnumbered by the ones that support the truth. And so in the long run, the majority vote will be wrong with a probability that decreases, tends to 0, as the size of the group increases. Actually, more formally, this is the theorem. The probability the majority selects the correct alternative converges to 1 as number n converges to infinity whenever we have a bunch of constraints. So here n is the number of people. Sorry?
I think it was a mistake. Yeah.
Was it? Where? Sorry.
No, I think someone unmuted by mistake.
Ah,
yeah.
okay. So n is the number of people in the group. And the assumptions are that each individual in this group takes an independent decision based solely on his or her own private information, the so-called private signal. Now we also have to assume the private signals are not totally unrelated to the truth, because they are like totally random, then nothing will happen. They are not obtained by flipping a coin. They are really evidence, like in this case, for instance, sampling from from a fixed distribution. So this means that the likelihood of each private signal to support the right conclusion of the two is bigger than 0.5. It might be very slightly bigger, but it's not equal or less, right? So it's not totally random. It's not like right. And well, there are generalizations of this theorem, but the way it's stated here, it actually, the original theorem applies only to binary choices, so like two mutually exclusive alternatives, right? The conclusions.
Is there a hidden assumption of kind of IID of this agent? So they have all the same probability to be bigger than 1/2? Or
yeah, well, so the way so the way I presented the theorem and the example that I had is IID, but the theorem is more general. The theorem is more general. Actually, okay, so this is not a mathematical statement I wrote here, but this is actually a correct statement of the theorem, and the theorem actually applies when all these assumptions are true. And as you see, the assumptions do not necessarily assume that P is the same. So actually it's a P for each agent. But as long as each agent has a probability to be right bigger than 0.5, the conclusion will work.
Yeah, so that was exactly my question. So if this depends on the agent and it becomes...
yeah, so it's not only in the IID trials, but the standard examples are typically IID. But I mean, like in my but it's not, the theorem is more general than that. And in fact, even is more general than this, because there are generalization ternary, and one can even drop independence a bit as long as there is not too much dependence. Only very small clusters of agents communicate to each other, it still is okay, but they shouldn't be too many. Anyway, so there's the theorem, the Condorcet-Joly theorem, and this people in philosophy of knowledge and group information and social epistemology make a big thing out of this theorem. So Goodin and List in particular and others used it to argue for what's called epistemic democracy. The idea that all things being equal in normal circumstances, because they know that there are exceptions, of course, democratic forms of aggregation of belief, such as voting, are conducive to truth. And the question is, of course, really? And here is a famous example. I did my PhD in Bloomington, Indiana, and that state of Indiana is famous from the fact that in 1897 has voted on the value of number pi. Well, actually, they voted on a solution proposed by some local mathematician of the squaring of the circle problem, solution that amounted to assuming that pi is essentially 3.2. And they were very proud of this guy, so because it was a local guy, so they wanted to make it a law. And it passed the lower chamber of the General Assembly, so to speak, of Indiana state in 1897 without a dissenting vote, so with unanimity. Then it reached the Senate and it nearly passed, but it was stopped in its track just because one senator, well, what happened is one senator called another mathematician from Chicago, and that one explained to the General Assembly that they are not allowed to do that, that essentially they lack the power, the legal power to define mathematical truth, no matter what the majority votes. Right? So it seems that maybe epistemic democracy has some limits. Right? So maybe an assembly of non-experts cannot decide mathematical truth by voting. But in other fields of inquiry, we do use such thing. So for instance, legal, factual truths about who is guilty, who did a crime, are decided, at least in the Anglo-Saxon jury system, exactly by this method. And by the way, I got this quote from Wikipedia. Right? So this is not a fact, or well, it is a fact, I believe, but the source of this fact is actually Wikipedia. What is Wikipedia? Well, Wikipedia is exactly the same kind of aggregation by non-expert voting or crowdsourcing. And we're talking about a historical truth here. And this historical truth, for all practical purposes, I know about it only due to this crowdsourcing. So can I trust it? Does historical truth, can it be established in this way by non-expert voting, by crowdsourcing? And why would that be different from mathematics? So the problem is, to put it in a nutshell, is that wisdom of the crowds is actually extremely fragile. Both forms of group knowledge can fail. And I have many examples in my slides of failures, and I mentioned here, but I will not be able to talk about all of them. So, and probably you know names from these names from your own readings, or so there is groupthink or bandwagoning. Essentially, there are social factors that are nothing to do with the knowledge or the facts that may influence other people's opinions, leading to herd behavior and kind of following each other. Another thing is group polarization. So this is essentially, after all the facts are communicated as much as possible and are debated, the group splits into peer groups or echo chambers or like radically disagreeing subgroups. One aspect of this is the so-called curse of the committee. Remember the hiring committee that I used as an example? If you've been in a hiring committee, you can, you know that it's not, it doesn't work as smoothly as you'd like to. People argue, they look at the references, they look at the papers of the candidates, they look at their CVs, and they may come, after all the discussion is done, and they may come to very, very opposite, very different conclusions, and they will stick with them. And they might not be able to agree at all. Another phenomenon is so-called informational cascades. This is like the first one, like bandwagoning, but it's not due to herd behavior. It's not due to some kind of social influence. It's so-called rational bandwagoning, because it's nothing fishy there, just based on their aim to, the agents only want to find the truth. They apply perfect rationality, as you'll see in some examples later. Their goal is nothing else but to find the truth. But somehow, this goal applied at the individual level leads, when they centralize by voting, to a conclusion that it can be the direct opposite of the truth. And another example is pluralistic ignorance. Essentially, it's a phenomenon I will not insist on this. That somehow some people have a shared situation in which they misinterpret systematically the behavior of the others in such a way that truths that are generally known by all are actually suppressed. They all know. It's the standard example is like the emperor's clothes story, right? So we all see that the emperor is naked, but somehow we suppress this because we think that it's on us. We are the only ones who see this, and the others see him. They are smarter than us somehow because only stupid people don't see the clothes, right? So then, all right. So what is a group's true epistemic potential? That's the question. How can we define that? Jay, may I ask a question? I don't know anymore when we started because of the delay, so I don't know how, like, when I'm supposed to stop.
Yeah, we started 10 minutes late.
All right, yeah. So, okay, good. All right, so what is a group's true epistemic potential? What is the group knowledge really about? It depends. So essentially, a group can be wise or stupid depending on many, many factors, and I'll mention some. It depends on the aggregation protocol. How do you aggregate? By communication, by voting. It depends on the social network, which essentially is first of all, the communication network. Who talks to whom or who shares with whom? And here are some examples of networks intuitively. There's a ring, there's a line, there's a fully connected graph in which everybody talks to everybody else, and so on. Some are very sparse, like the ring and the line are very sparse. Each agent talks to two other agents, no more. And some are very connected. It also depends on the degree of mutual trust between agents, but also on what I call the agent's epistemic interests, their interrogative agenda, what questions they aim to solve, what problems or questions they aim to answer. Right? So what do they want to know? What is relevant for them in the sense of knowledge? Because that may limit their ability to learn from each other. So failures of the first type of group knowledge. So not only the factors, right? So the factors that I mentioned, but one could put them together into something that I call selective hearing. Selective hearing is essentially people talk over each other. So, and that's in a way perfectly rational, because they might not be interested in what others have to say, might not hear it, might not want to hear it, and so on. So they process only the information for various reasons. They process only the information coming from some sources and not the others. Let's say their friends, or the sources that issue things that are relevant to them. Or in the worst possible case, the sources that issue statements that are consistent or agree with their own information or their own beliefs. That's the worst, because then you never learn much, right? If you learn only things that are relevant to you, even if they disagree with you, that's not so bad. If you learn from your friends and not from theirs, that's maybe not so bad. But if you only agree, process the information consistent what you believe already, then it's a dead end. Okay, so maybe I will go a bit fast over this. So let's call these agents friends, but typically they're really sources, the trusted sources for each agent, his friends. And an epistemic network is just a model, an epistemic model, like a set of states and the equivalence relation for each agent, which in addition, we have a relation between agents, between pairs of agents, but it's state dependent. So the relation might differ from state to state. Let's call this relation friendship or access, right? So it tells you that in state S, agent A has access or trusts or is friends with agent B. So processing information that comes from B or from C, but not from others. Right? So this is this state-dependent friendship relation. And for each given state S and each agent A, we can collect the friends or the sources of that agent into a set, the set of A sources in state or friends in its state, Fs of A. And typically in such networks, there are two requirements typically imposed, namely in distinguishable states, right? So if two states look the same to me, then my friends are the same in both, right? Or my sources, right? So these two indistinguishable states for agent A, then the F of A's are the same. This says essentially the agents know who their friends are, or they know their own sources. They know, that might be not always true, but it's a convenient assumption. And the other one is more about access, so to speak. It says like an agent can access his own information always. Right? So the relation is reflexive. That's not absolutely necessary, but it says simplify some things. Now, how can we define in a network the potential knowledge of each agent? I will call it K infinity from knowledge, but infinity. All the knowledge that this agent will be able to gain within this network only. Well, you start with what the agent currently has access to. To start with, we can assume she only has access to her own opinions or her own evidence. So F0 of A at state S consists only of A. And then you iterate. At stage n plus 1, Fn plus 1 of A at that state is the union of the sources of all your sources. So yeah, you look at the sources or friends of agent A, all the B's, and you look what knowledge they got or what sources they get at the previous level, at the n level. And you get them all together, you get the n plus 1 level. Right? So you see what this does, it explores the network more and more in depth, essentially constructing a larger and larger social circle, essentially in this mediated manner, right? You get from your sources, you get implicitly after a while information from further. And F infinity is the union of all these. Right? So that makes sense. So now, instead of distributed knowledge, we can look at distributed knowledge, so to speak, within your social circle, which essentially says at stage alpha, which alpha can be a natural number or infinity, I define an alpha indistinguishability for each agent that essentially takes the intersection of all the relations as in distributed knowledge, but not for everybody in the world, but for everybody in your alpha level social group, so to speak. Right? And then using the same way as we did for knowledge before, or distributed knowledge, using this equivalence relation labeled alpha, we get Ka, there's A missing here under K, knowledge of level alpha for an agent A, including infinity, right? So I'm particularly interested in K infinity, Ka infinity. So this potential knowledge in the network is the Ka infinity, and essentially amounts to distributed knowledge among all A's potential sources, like sources and sources of sources and so on, a social circle. And now, as for distributed knowledge, communication helps you to actualize potential knowledge. But now this communication is more, it does it in more stages rather than just, because you're not allowed to communicate in a network. You cannot just access directly far away nodes or agents, but only your friends or neighbors or so, direct sources. So let's define, like we did before with this sharing action, another operation on models, communication, that leaves everything the same, except changes the epistemic relations, this kind of knowledge relations or distinguishability relation for each agent, to a version, another version of them, prime. And what this other version is exactly, well, the next stage, so to speak. So something is indistinguishable for you in the next stage, if it's indistinguishable for everybody in your group of one-step neighbors or one-step friends. So essentially this says, right, I will not be able to distinguish, even if I'm talking with my friends, these two states, if none of them, my direct friends, can distinguish them. Okay? But of course, now this iterating this does more than in the sharing. When we did the sharing action, was one step only, sharing everything you know with everybody else in the group G, bye-bye. Here, this communication can iterate and produces more things at further steps. And you can now see that in a way, the level n+1 knowledge is encoded by a step of communication and then the previous level of knowledge. Right? And the infinity corresponds to, well, I didn't explain what this star means. Star means essentially the limit of all this stuff. Right, so it's the, technically speaking, the reflexive transitive closure of all this all the steps, any finite number of steps. So if by any finite number of communication steps you get to know P, then this means P is potential knowledge of yours. All right. And now, depending on the network, potential knowledge within a network may fail way short of full distributed knowledge. Right. So that's the first limitation that networks pose to our group knowledge. But of course, things get much worse because remember selective hearing. So if we take into account the agent's agendas, like their questions, then further limitations will be put into place. So essentially, we implement the selected hearing principle by formalizing the notion of epistemic interests, like what are the outstanding questions that the agent is interested to solve, the issues. And that's joint work with people mentioned here. I will not do this in detail, but suffice it to say that to formalize this, we need another piece of information, namely, in addition to this partition that or equivalence relations that reflect what each agent knows, the structure should tell us what they want to know, what is relevant to them, right? What they're epistemic, what they would like. So we have another relation, another equivalence relation, one for each agent or another partition, this approx here, which is typically, yeah, so what you know is part of what you want to know, but not the only part, right? Right? So, so we have some constraints between these two relations, but they are not the same. And now these constraints will also apply to the learning or communication. When something is communicating from your sources, some piece of information, you will be learning only what is relevant for you. So the proposition that the sentence that it said might not respect fully your partition that reflects your interests or questions. And you round up to the cell of your question partition, essentially taking all the relevant consequences of what you hear. So you hear something literally, but actually you process less because you round up the information to a weaker proposition, if you like, a larger set of states that it's made of cells of your question partition, right? So respects those cells, doesn't cut through corners, through the cell of your question partition. So this means typically you learn less than what you hear. And everybody does the same. Everybody, maybe they all communicate publicly in the group, but they all hear the same, but they all process things differently depending on their questions. And that may actually be shown to lead to radical disagreement based on the same evidence. So we can define a notion of epistemic potential or group knowledge that essentially processes this. And essentially this KG now group knowledge is whatever will become common knowledge after everybody learns from the others everything they can, but rounds up to what's relevant to them, right? Learns in this way, in this selective hearing way. And this potential knowledge will typically lie between common knowledge and distributed knowledge. So will not be as bad as what was already known to everybody before, but will not be as good as the full distributed knowledge of the group. It will be something in between. So, right? And in some extreme case, it will coincide with one of the two, right? Typically, essentially, you can have the extreme case in which every agent is interested in everything. So he is questioning everything. He wants to learn, yeah, so essentially his question, the partition for his question is essentially made of singletons. So it's like every cell contains only one state. So he wants to learn everything about the world. Then they will learn everything from each other, right? So if they talk to everybody else in the group, then their potential group knowledge is exactly distributed knowledge, will be maximum. There is the opposite case in which each agent's questions are orthogonal to what the other agents have to say, so to speak. So then they will not typically learn much from each other. So the group knowledge will be minimal and will amount essentially to what was known already in common from the beginning, the common knowledge. And that explains the so-called curse of the committee, that after a lot of exchange of information, a lot of deliberation, committees many times tend to agree only on what they could have agreed from the beginning, the only few things that they agree to start. All right. I'll skip a few of generalizations here, and maybe I don't want to talk about echo chambers, although. So I want to move on to the second type of group knowledge, the statistical one, and to show examples in which of failures of this type. Right? So, so the failures of this type can be due to either the data itself, because remember, the opinions are based on soft evidence in this case. They're not as 100% accurate necessarily. So there may be that the evidence, the private evidence they get is already biased or wrong or insufficient systematically. So that the group, even when they pull out, they will not cancel each other, these biases, but rather they will reinforce each other. So that's a source of failure. Another source of failure is that when the agent's independence is breached, right? When they talk to each other before the voting, they influence each other's opinions by, for instance, saying them or showing some part of the evidence. And that will give rise to informational cascades. So why the Condorcet-Jury theorem fails in this case is because, of course, the Condorcet-Jury theorem assumes independence, at least to some extent. And without it, you may get... so let's look at the urn example. Remember the two urns, W, majority white, W, and majority black. And let's see what happens if we allow some communication. So remember, each agent is introduced in the room. They take a ball, they look at the color, put it back, and then they make a guess. and the guesses are recorded in a big book by the experimenter. But now the guesses are announced to the others. So the big book is open. So after the first guy gets in and out, the next guy comes and he sees the guess of the first guy. It's on the, it's, if you like, on a blackboard. So, and so on. The third guy will see the guesses, white or black, of the opinions of the first two, and so on. So they are allowed to communicate in this way. And now, the opposite of the Condorcet-Jury theorem happens. Not only that, no matter how the largest group, the group is, and no matter how big N is, not only the majority will not necessarily get it right, the right belief, but there is a fixed non-zero probability, which is slightly over 1/9, that the whole group will unanimously get it wrong. No matter how big the group is, you can enlarge to millions of people. So total failure of epistemic democracy, right? So I hope you understand.
How does this communication work exactly? So
you can imagine various scenarios. The scenario I imagined was that each agent is allowed to make a guess. Is the urn majority white or majority black? And the guess is recorded, say, on a blackboard in that room. The next agent enters, he sees the guesses of all the previous people. Another way is to just publicly announce by a megaphone. Like the moment one guesses, the experiment announces like, hey, people, number one guessed W. The cascade will happen in either of these.
But so how is the vote of the next agent influenced by this information? That is not clear to me.
It's influenced by, we assume the agents are perfectly rational. They can use probability theory, essentially Bayes' theorem, so they can compute what's the most probable urn, given their evidence, right? So let's see a specific scenario. So let's suppose the urn, in reality, the urn is majority white, W. But by chance, by mere chance, the first two people happen to pick a black ball. This can happen, right? 1/3 probability, because it was only one out of 3, black. 1/3 times 1/3, 1/9 probability. I claim that from that moment, a cascade will start that will make everybody vote forever the wrong urn, namely black. By the way, the cascade can even happen also later. So as a result, the probability is not on 1/9 that this happens. It's higher than 1/9 slightly, but okay. What will happen next? So you can use Bayes' theorem, as I said, or you can just use your intuitions. In this case, it's not so. So, right, so each of the two first people, they see a black ball. The second even sees the previous guess, that the other guy guessed black. So presumably, being a rational one, he saw black. So the second guy sees, so to speak, 2 black balls or 2 black eggs. So they both have the most likely urn according to each of them is black, majority black. You can again compute this by Bayes' rule. The third guy, the third guy sees 2 guesses, black, black, and now it doesn't really matter what the third guy color is, like what the color of the ball is. Even if she sees white, she has 2 pieces of evidence for black, the previous 2 guesses, and she has 1 piece of evidence for white, the white ball. If you apply Bayes' rule, you see that, or just intuitions, that it's more likely that the urn is actually majority black. And that's an objective fact. It's from the perspective of her information, that's the truth. That is the most likely outcome. Of course, if she sees a black ball, it's even worse. The probability is even higher that the urn inside will be majority black. So no matter what, she will guess black, because that's the rational guess for her, if she wants to get it right and knows probability. But we prove this. We just proved it. Oh, well, sketch the proof. Given this proof, this means the guess is uninformative. It doesn't matter if this guess is announced to everybody else after that. It's as if it didn't happen, because they could have computed. For the fourth person, it's enough to look at the first 2 guesses. The third is redundant, because it doesn't give you any more information. So the fourth person will be exactly in the same situation as the third from the point of view of her information. So she will also, by the same reasoning, guess black. They will all guess black forever. Unanimously, the group will vote for black. And this is after millions of balls have been examined, and out of the millions, probably by law of strong numbers, the strong law of large numbers, probably the majority of the balls were of color white, because actually there are two rather than one. But it doesn't matter, because by just communicating their beliefs in this way, they influenced each other, and not in a stupid or herd-like manner, but purely rational. Each of them does a rational calculation. What's the most likely earn? And it happens to be black. And they all get it wrong. All right. So that's actually a famous experiment that was first described in the first paper by economists that describe informational cascades, and they argue that that is rational, completely rational. There's nothing wrong with that, except that, so essentially they were trying to show that in economics, bad things can happen, like that will distort information in the market, even if all agents are perfectly rational, like the ideal game theorists. And then it was done in laboratory, and of course it works just as well. Now, people objected to this because my talk is about what logic can do, so I'll take 10 minutes to do, so I'll be maybe 5 minutes late, to explain a bit why, like what logic can do, because this was already done by this economists using probability theory. So yeah, the Bayesian analysis says the answer is correct. There is nothing you can do in this case. Essentially, it shows that if you individually, each of the members of a group wants to find the truth and is super rational, that's all his goals in this case, then that's not necessarily that means that the group will be rational, will proceed rational, will converge to the truth. It depends, right? But well, yeah, so there is a tension between individual rationality in this case and group rationality, and that's the conclusion of now people doubted this proof, saying, look, there are lots of things that can go wrong. First, some people doubted, they say people are not perfect Bayesians anyway, so maybe in reality they can do better because they don't do probability so well. We know that. All right. Others said, yeah, but actually is the opposite argument. I mean, people are so smart, rational people are so smart, at least ideal rational people, the agents, that they shouldn't fall into this trap. Somehow they should stay through it. They should be able to reason about the situation at a meta level and to realize the possibility that they get into this cascade, just like we did now when we did the proof. And taking this into account, they should be able to refrain from these guesses, the wrong guesses, and get out of the cascade, not get into it. So essentially the argument says that if we take into account higher order beliefs, like beliefs about what's going on around in this game, and why the other people guessed, like what explains the other guesses, the black, right, before me, and what do they think about the others before them, and so on, all this higher level rationality that people in game theory talk about and logicians also formalize, then we will not get into the cascade. And by the way, there are situations intuitively in which this is correct. For instance, a standard example, I go down it happened to me in a train station in the Netherlands, and it's very crowded. I'm in a huge hurry because I'm late for my own talk. And I try to look for the exit, and it's like very crowded. And but somehow I see that a large crowd from the train, they all pour down somewhere to the left of the station. So I assume they are all looking for the exit, and they follow others that know that the exit is there, right? Or they looked at some signs better than me to pay attention. So I follow the crowd, and typically this works. I mean, with high probability, I will get out. Now, okay, we twist this to make it a cascade. In reality, at the end of that crowd, an accident happened, in fact. A guy was hit by a train. And the first onlookers gathered to see that or to help, the others to see the first, and so on and so forth. And after a while, people just follow the others, thinking that's towards the exit, like me. As a result, there's a cascade that points to the wrong exit, so to speak. What can you do to stop this cascade? okay, people are not super rational, but you can make them super rational by announcing them. So you take a megaphone, you being the railway master, the station master, you announce by a megaphone, by a big people, if you are looking for the exit, look for the signs, depending where you are. Do not follow the crowd, that the large crowd in a certain part, because they're having an accident. So just go away if you're not interested to help with the accident, and look for the signs to the exit. This will stop the cascade. Right? So making people aware of the problem, or the potential problem, is enough in many cases to stop the cascade. So they will look for the signs, the majority of the people, if the ones who want to get out. But this doesn't work in the Earn example, and one can prove that. So how can you prove that? Well, we use epistemic logic. So epistemic logic has these features, although I didn't explain that actually these models are very powerful that I described, these very simple models. And they're probabilistic extensions to deal with the probability, as I mentioned, but essentially they incorporate not only what the agents know, because it's a global structure by chasing the indistinguishability relations, going from a world to the indistinguishable by agent A, and from there to the ones indistinguishable by agent B, and so on. You can actually compute knowledge about knowledge about knowledge. You can compute all the levels of knowledge about. You can compute what is common knowledge, as I explained, and this. So epistemic logic incorporates all this higher level of rationality about what is the case, what the others think about it, and so on and so forth. So automatically assumes these agents are superior. And now dynamic epistemic logic, the kind of branch of epistemic logic that deals with these changes on models, actions, adds similar levels of mutual knowledge all the way up to infinity at the level of the actions or the protocols that we are following. So essentially, it can say that I know, or I know, or we all know, or it's common knowledge that this is going on. That, for instance, the setting is such that the Earn is like that, and the others have to do that. That all this is common knowledge. It can also say that it's common knowledge because somebody announced us that there is a possibility or non-zero probability, 0.9 or more, or 1/9, sorry, or more, that we may be in a cascade. So it can say that, it's built in the models. So as a result, if you reprove the same cascade in this setting, then you essentially neutralize the argument, the counter argument, because essentially you showed that even rational people with infinite abilities of reasoning about others and about the whole protocol, what's going on, while being aware of the fact that they are in a cascade, still will vote for black Earn, because that's what the information points to. And okay, I have to skip the proof because I'm late. So I'll take only 2 minutes, as I announced, to finish. So I'll skip the proof, but yeah. So we have models that deal with that, dynamic models that change in such a way that you can prove by induction that that even if they are aware of this whole situation, of this possibility of cascade, they will still unanimously vote for the wrong Earn, given their information, because there is no way out. And that's perfectly rational. What could be the solution from this dilemma? Can logic help to get not only to analyze and to prove these things, but also suggest ways to get out? Well, there are issues of mechanism design. You can change the rules of the game, so to speak. So one way is, for instance, to change a social network, to change who communicates with whom, or to allow them to do joint communication strategies, protocols that they are somehow bound to each other to do. So for instance, the original network, the case in which everything worked out very well, I would call it the Condorcet network, was no communication was allowed. Everybody had only access to their own private evidence, and at the end, the votes were counted. And that works perfectly, remember? For the group, not for the individuals. The individuals didn't have much information. They could easily lose the game, but as a group, they win. So that's called the Condorcet network, because the Condorcet strategy essentially consists of right? So doing guessing what you see essentially works very well. The other case was in which everybody announced to all the subsequent ones. So you have a connection in which everybody is a source of information of his own beliefs to the subsequent guys, right? So that's a sequential public announcement. And we saw this leads to a cascade. But in fact, you also saw that the third, I mean, from the third guess was irrelevant. So essentially, you can reproduce the same cascade with only minimal communications. As long as everybody sees two previous guesses, you're done. All right. You can change the payoffs. I didn't talk about payoffs, but there's a game theoretic, right? So the intuitions, the implicit assumptions were that actually people want to tell the truth. When they announce their guess is the correct guess, the one they really believe. But why would they do that? Probably because they are rewarded for her performance. So at the end of the game, they will get a sum of money if and only if their own guess was correct. Then they will be Bayesians. They will do the Bayesian strategy. They will compute the probabilities as we mentioned, and you can show in that case the only Nash equilibrium of this game will be the Bayesian strategy, which leads to the cascade. By the way, is the wrong one for the group. By changing the payoff, you can make them a bit more interested in the group's happiness. So, for instance, of course, the easiest is communism, right? So you change the payoffs. I mean, mind communism, spiritual communism, not the enforced one. So you change the payoffs. Agents are rewarded if and only if the majority vote will track the true earn. So it doesn't matter what they themselves, if they get it wrong, who cares? But if they guess in such a way that the majority will get it right, then each of them gets a sum of money. Otherwise, nothing. All right, then you can prove that the cascade will not fall, because essentially they will not have any incentive to announce their true belief about the earn. Instead, they could use some other ways to essentially communicate in such a way that their guesses give more information to the group. And what information you want to give to the group? The color of the ball that you saw, the piece of private evidence. So you'll only guess exactly what you see. That doesn't mean you believe it. You don't believe it. You're actually almost sure that it's wrong, that the earn is the majority black. But since you saw white and you're interested in the group to get that, you guess white. That ensures that right? So that's the Condorcet strategy. In contrast with the Bayesian strategy, it always disregards the other piece of information from the others, takes only my private one, and disregards their opinions and only announces that. You may lose, it's very likely that you may lose yourself, but since you're rewarded for the group will win. And the most interesting case is if we reward players for somehow we give them two rewards, one based on the individual guess, if that one is correct, and the other one, another sum of money, if the majority vote is correct. Now, depending on the amounts of the money of these two rewards that I may get, better strategies may work than both the Condorcet and the Bayesian one. For instance, here is another strategy that does, if n is very big and the rewards are balanced, then does better than both, namely, right? So if n is very big, then n over 2 is also very big. So what we can do is we apply one strategy half the time in the first half. Essentially, we apply this one, Condorcet strategy in the very beginning. Essentially, everybody just disregards the opinions of others, even if he sees or doesn't, just guesses what he sees, the color that he sees, until you reach the half. By then, you have enough numbers that these guesses now probably, by the law of strong numbers, probably approximate the two probability. So with very high probability. So as a result, it's stupid to keep going. Then the rest of the people over n, from n half to n, can use this information. Now they can do majority voting. So you see what is the majority voted till n, and that's very likely to match the true earn. So they will all get a so they will all get a good outcome for themselves, but also for the group. So that's a better. And now, if the n is even bigger, it's actually better to stop at n over 3. Then, right? You get even a bigger total reward on average. So, so you can study this, and this is in the thesis of my student Andrea Chimescu. All right, I had more to tell you, obviously, but I would like to stop here because, I ran out of time, and it'll be better if we can actually have some discussion about this or questions. So thanks.
Thanks very much, Alexandru. So,
Soroush, I cannot hear you.
Oh. Thanks, Alexandru. Can you hear me now?
Yeah.
Let me just mute. So questions, comments, please. There is one in the chat. I will open my voice so you can hear them. Okay, Jens, do you want to ask the question right here?
Yeah, am I audible through your microphone?
You should be.
Yeah, it's maybe a little bit silly, but I was wondering if you have some sort of exploration mechanism in the guess. So you guess based on all the information you have with some probability 1 minus epsilon t, and with probability epsilon t, you guess the color you have.
Yeah, I understand the question. Sorry. It's a very good question, actually. And so there are studies of this kind of variations. You can think, I mean, logically speaking, it doesn't matter why would they do that, but it matters what do you, but of course you can explain that behavior. The one explanation would be to change the incentives, the payoffs, in such a way to make the exploration worth it. Another way is to just assume that some people are like that. I mean, not everybody has to be a rational, perfect Bayesian. Maybe they just don't care and they like to explore. So, and maybe that's better for society. So, right? So you can plant irrational agents and see what happens. And irrational agents could be people like, say, the philosophers who never care about the opinions of others. They only guess what they see, what they believe. Or the explorers, the ones who, you know, take some chances, but they take a high enough chance to get it wrong because they want to explore. Anyway, so you can make these variations and to see what happens. And indeed, depending on the parameters, better things might happen. It says that you may increase the likelihood for the group to get it wrong, right? And so this is another way to do this what I mentioned as mechanism design, which would be from the perspective of society or the government, tweak things around to try to achieve in a non-risky way as much as possible a better outcome for the group. For instance, plant some government agents that systematically guess totally random, or systematically disregard the others or explore, right? So these are people who are not in for the money, even if the payoff says that they don't care because they have another, right? So they just do that. Or crazy people, right? Maybe it's good to have crazy people in the society because they will do the exploration for you. And that actually might benefit the rest, right? Because already a few such different guesses in the list might make the others change rather than. So it's true that that things are more, I mean, more interesting if you allow that irrationality, so to speak, at the individual level.
Okay, Robert, please.
Yeah, I have a question about these, how are they called? You know that after, if you have discussions with others, or that in time, people disagree more and more, right? Some people say that's actually a fact, that in these echo chambers, right? That due to echo chambers, people disagree more and more,
yeah, and
become more and more radicalized. Can you explain that with your formal model?
Yeah, so these are a bit of, it's unpublished work. Well, it relates to the agendas, which is published work, the interrogative agendas that I did mention, but it's also some other components that are not published. And I had some slides about it. Maybe I should put them. Anyway, so I had a few slides that I said I'm going to skip, was about echo chambers and stuff like that. So, so essentially there we tweak the assumptions to make agents not only select the information based on their prior beliefs or prior agenda, but also to have a mechanism of source selection or friend selection, which I think is pretty realistic, especially on Facebook, which in a different round, you select the friends with which you agreed before, or from whom you got relevant information before, relevant for your interest. So there are various variations of this. It could be that you agreed or you didn't necessarily agree, but it was relevant to you. As in, like, maybe you disagreed radically, but it looked relevant to your question. And these kind of variations will can be shown to lead to what you're mentioning, essentially radical disagreement and the splitting of the group in smaller clusters that are more and more extreme, although in principle they would have, access to the same facts. Of course, yeah, we didn't take actual deliberation in our model, like debate, because that's a complicated one. How do you model debate? But just fact, like kind of belief communication. I communicate my beliefs, you believe, and that's it. But then the process is done by the selection principles. But you see that as sources get deselected as my sources because they are not relevant, the amount, even if we don't, I don't automatically delete the people I disagree with, but just because I delete the ones that are not relevant anymore, then the amount of serendipity among my sources decreases, right? So it's very much like Amazon recommendations for books versus going into an actual bookstore. When I go to an actual bookstore, I'm looking for certain books, but actually also screen around and I may get information that is totally originally look totally irrelevant, but I might get interested in it, and then actually that might eventually change my information standard minded. While on Amazon recommendations, they are based only on previous search.
But what I find potentially interesting is that I think many explanations of echo chambers, right? They say, oh, this is due because they get different information. Right. Yeah, and your explanation would say, and that actually seems to be false, right? Because if you look at the data, people just look at other data as well, other information as well, also from the other side. They just pick up different things from it.
Yeah.
So that might be.
So my impression is that, I mean, of course, our models are simplistic still, but that there is something deeper than that. Of course, people have also different information, but I mean, even if they try, there is the processing of the information that is a big problem, and then the feedback loop that feeds back into the network as in the selection or deselection of your sources based on not even conscious bias, but just lack of interest. Like, look, this is not relevant. Maybe I will not go to this site anymore. But that can, which by the way, you have to do because maybe at some point you reach too many sources, too many sites, too many friends. And then that's not physically, you cannot handle it. So then by doing this, you try rationally to, and it's a perfectly rational process because, right? So maybe you want to find the truth, but I mean, some things are less truthful than others in past experience, some things are not relevant. So then by this balancing, you can actually screen yourself from a part of reality and reduce your interaction with the world at large in such a way that you become part of one of these, and it seems in a way rational from the internal perspective of the agent could look perfectly rational. Once again.
Okay, more questions, comments?
I had one more question about this example of the urn, if I may.
Go on, yes, of course, Frank.
So you can represent it that you are growing a graph somehow of opinions of agents that are connected to each other. No, for instance, in the simplest setting, no one is connected to no one. There are settings then where you have to kind of grow a one-dimensional like graph. So for what kind of graphs do you at the end obtain the truth? So I mean, if there are no connections, you obtain the truth. The true characterization of the kind of graphs that
so we didn't do a systematic exploration of all the graphs. Probably this is also beyond mathematical, logical, analytical, what you call analytical, I would call logical methods. It's more, so people that do, not necessarily for this example, but related example, people who do computer simulations did look at this issue. Like essentially they generated automatically like large number of graphs of finite, but and then they used so that they try to get some conclusions from this. And essentially the conclusions, which again, it's not a proof because it's based on their experience plus these simulations. I would like to have a logical proof of that. The conclusion seems to be, and I had about this on the slides that towards the end that I missed, that very sparsely connected graphs are very accurate in the sense of if there is any, in the end, conclusion, like the majority, unanimity, whatever gets to a conclusion, then it's very, very probable to be the right one. So they are accurate in that conclusion, but extremely slow to ensure any kind of convergence because they may take forever to get anything. The completely connected or as much as connected as possible graphs are extremely fast at achieving convergence, but are not very reliable. And that the optimum best seems to be something in between, like some kind of mildly connected graphs. And
so can it happen that this
yeah, so there's a guy at CMU, what's his name, Kevin Zollman, and his collaborators that did these investigations, as I said, using, and then they very nice paper about that, a famous one. So yeah, I don't know if the conclusion is generally true or more to be more correct, in what conditions it's true, because it all depends on the assumptions. For a logician, this is important stuff. I don't have a proof, but I believe they are onto something. And yeah.
And yeah, so a bit related to that, how much is the influence of adding some, I mean, this is probably related to a previous issue, how much is the influence of adding some individuals with random opinions?
Yeah. So again, I know things
not influenced by anyone else, just random.
Yeah. So the things done again with computer simulation that planted this kind of run also try to kind of to explore this setting. And again, you don't want too many of these because right, and the conclusion is random. It's like the majority will be formed randomly. You just want to have a moderate number of them, and it also matters where in the network you have it, right? Because right, so how late did they play a role? Because yeah, so when this is sequential communication, it matters who is the first and so on. So it matters them to be at the. So there is even somebody, Vincent Hendricks, a philosopher, who talks about these bubbles or informational bubbles, or as it's important when you burst them to place a piece of information or a irrational agent at the right moment in the bubble, not too late, not too early, right? Because too early might have no effect whatsoever over the cascade that is forming, and too late might be too late to repair the problems that are caused by. So then you burst the bubble, but of course, and here's some examples about this, but no systematic exploration as far as I tell. The problem with these studies, of course, is that in reality, we all live in a world that is nowadays the super connected graph. That's it. We can't escape it. So right. So we used to live maybe in the beginning of the modern scientific era in a very sparsely connected world in which people did their own research and they communicated by letters from time to time. And now we live in one in which we get all these other opinions and stuff instantly, and it's very hard to screen them off. So saying, okay, I would like a more moderately connected graph. How do you get it? Because we are in this super connected one, and that's part of the problem. Right? It's what makes it very fast and potentially very catastrophically inaccurate from the point of view of tracking the truth.
Okay, Robert, do you still have a question, or is it the raised hand is from the last question? Oh, he's already gone. Okay.
It was a mistake.
Yes, any more questions, comments? Okay, then let's thank Alexandru again.
Thank you.